let's move to number 2. A new kind of toy ball advertises bounce perfectly elastically. Okay, first of all, I don't think it's possible to have perfect elastic unless it's ideal case. Maybe in an ideal gas world, it's a perfectly elastic. Right? But and of the hard surface, and students suspect, however, that no collision can be perfectly elastic. The hypothesis that collisions are very close to being perfectly elastic. On low speed, that kind of makes sense because you lose less energy. Most of the energy you lose by heat, sound, and probably in low speed you do not generate much of heat or sound. So it could be think as elastic collision. But in a high speed, you'll definitely generate bigger heat, more heat and more sound, sometimes more light, like sparks, that will use the energy out, right? So it can't be really elastic. Now, but they deviate, so they are differ more and more from perfectly elastic. So that's actually a good hypothesis. Design experiment to test the student hypothesis about collision of the ball with the hard surface in a school laboratory. What quantity to be measured? So how do you measure if a ball is elastic? Okay, elastic collision means what? Elastic collision means before collision and after collision, momentum m1 v1 has to be equal to m2 v2. I'll guess I have to use magnitude, okay? Or you can say so momentum does not change, okay? But let me get rid of this because it's not just regular collision, because you're colliding with the wall. So I guess the better explanation is just in terms of energy, okay? So before you hit the floor, this one has kinetic energy, so I'll just say 1/2 mv1 squared, and after the collision it has to have same energy, which is 1/2 mv2 squared. So basically the magnitude of v1 has to be equal to magnitude of v2. That's what I'm trying to say. Then what's going to happen is you have potential energy h mgh, and becomes kinetic energy of 1/2 mv1 squared. Once it bounces, it becomes 1/2 mv2 squared, and it converts back to h, and you repeat this boom boom again. Okay, you repeat this process again. But if you think about it, this only happens if while in this collision there's no heat or no sound or any types of energy loss, then this is possible. So either you can measure velocity before collision and velocity after collision and say they are equal, or you can measure height initial equals height final that you can measure, right? So because these days you can use like you can use motion sensor. Sometimes they use motion sensor that actually directly calculates v1 v2, or you can use h1 and h2. So what could be used? You could use initial velocity, final velocity, or initial height and final height. But here I'll just use initial height and final height, right? So I'll say measure of initial height, measure of final height. What equipment will be used? You can use measuring tape, or a small distance you can use ruler. So I'll use or meter stick. So meter stick or ruler or measuring tape. I think all of them works. Describe procedure to be used to test. So hypothesis. So you measure initial height and final height in a various height, right? So you have to try, like, I'll give you a number like 1 meter, 2 meter, 3 meter. So I drop at 1 meter height, I drop at 2 meter height, I drop at 3 meter height. So, and you're trying to see where this data goes, right? And you may want to say, I'll repeat this 1 meter like 3 times, 2 meter 3 times, 3 meter 3 times, and use the average to use the data in the plot to reduce the error, right? Okay, so that's how you elaborate. Describe how would you represent data in the graphical table. So that's, I already showed you initial height, final height. Determine whether the data is consistent. So if it's elastic, that means initial height equals final height. So if when I drop at 1 meter, probably it'll go to 1 meter. So somewhere, so I'm expecting something like this. 2 meter, if it's perfectly elastic, that will bounce back up to 2 meter, which is probably not the case. So it'll be probably lower. And 3 meter is even further deviates, right? So something like this type of data I'm expecting, okay? So this is consistent. If that happens, that's consistent with the student hypothesis. If this somehow if we come out like this, that means it's elastic. And let's say you come something like that, which is not possible. That means it's like explosive. Like the ball has its own like gunpowder. When it bounces, this shoots up faster. Then you'll get something like this, but not in normal situation like this, right? A student carries out experiment analysis to discover student immediately concludes something went wrong. So if it's immediate concludes something went wrong, probably that's the case where you gain more kinetic energy after the bounce. That means while bouncing, somehow this ball gained energy through, well, the only thing I can think of is like a gunpowder or some types of hidden springs here. Maybe it pushes with the bigger forces, so it gains speed, something like that. Okay, so it's not normal. Okay, it's all be against, what did I call it, against the law of physics. All right, give an example of graph that table indicate nearly elastic behavior lower speed but appears violate the basic principle of high speed collision. So I'll say something like that. Either you can use H final, or you can say VI and V final too if you want to say, or you can say 1 of MV1 square, 1 of MV2 square if you want. Either all of them will actually give the same graph. And state so you will say conservation of energy, right? Conservation of energy. And prove why this way. So energy is added after bouncing, which is not true, okay? Which can't be possible. So that's how you elaborate this, okay?